Hello, good afternoon, good morning. I don't know at what time you're watching this presentation by Hubert Klahr from the Max Planck Institute of Astronomy. Which was brought to you by invitation of the organizers of the wonderful Lawrence workshop in Leiden. My topic is the formation of planetesimals, and I'm investigating this formation of planetesimals in a non-laminar solar nebula. So if I only have like a minute or two to explain you what I'm doing, then I would show you this movie here. So I'm showing you here a hydrodynamical simulation of a disk around a young star, and the illumination of the central object, the sun, the young sun, is imposing a temperature gradient on this disk. And as we have been showing a couple of years ago, and other people have also shown the same thing, this radial temperature gradient will, under the right conditions, especially the cooling time, produce vortices and other things in that. So what I show you now is a short movie on exactly this subcritical baroclinic instability. I put some dramatic music in the background just to entertain you. Maybe you are watching this movie late at night or very early in the morning. So you see here that in the disk, the radial temperature gradient is creating large-scale density waves, which we had been showing in red. But at the same time, if you are calculating the local vorticity, you are checking that there are local gigantic storm systems forming in this disk, anticyclonic vortices. And these anticyclonic vortices are locations in which you are collecting pebbles, in which you are concentrating them to levels that even with a low average pebble to gas ratio, you can form planetesimals. The outline of this presentation is that I want to tell you 4 or 5 different projects that we think are helpful in closing the loop between the initially turbulent state of a disk, the evolution of solids in it, and ultimately the building of a planetary system. So in the beginning, I will talk a little bit about recent results on vertical shear instability as a hydrodynamic instability operating in certain regions of the disk around a young star. I will show how it is creating vortices to trap our pebbles, and also how it leads to an angular momentum transport which we can parametrize in terms of alpha, so that we eventually will know, or do already know, maybe we are right, how big the viscosity is as a function of the disk temperature and of the local temperature gradient. Work that we have been publishing in the following things by Natasha Manger, a former student and current postdoc collaborator of mine, as well as Thomas Pfeil, who's now a PhD student at the University of Munich. So in the next step, I will present you some really new results, which I've been just presenting here on a workshop in Ringberg, which is the vertical shear instability and a second instability, convective overstability, for long cooling times, and that they actually operate in coexistence. So a version of the vertical shear instability in a cooling time regime which was unheard of before. Work which is based on old stuff, so Klahr and Hubbard and Vlad Lyra also worked on this in 2014, and as I said, a paper which I'm just putting the final touches to, but I'm meanwhile relatively sure about the results and nobody has contradicted me so far, so I'm courageous enough to present here some of these results. Good. This leads me over, when we have already now our zonal flows and vortices in disks, then the question is, of course, how planetesimals are forming in these zonal flows. And this is work in collaboration with David Carrera and friends. And there is a paper in 2021, and in 2022, just recently, he put up the follow work up on AstroPH. You can check it out there. So if you're forming planetesimals in zonal flows, then of course still the question remains, what is the size of the things which you're forming there? A typical grid simulation ends up with a huge cloud of material, but whether there is something forming out of it has to be solved for differently. So initial mass function for planetesimals is work we have been describing in Klahr and Schreiber 2020 and also 2021, which will be also then a brief part of that presentation here. And finally, I come from the planetesimals in combination with pebbles, which are abundant in the disk still, to the formation of embryos. And this is work done mainly by my PhD student, Oliver Völker. Let's briefly start with simulations by Natascha Manger on the vertical shear instability. This shear is unstable under certain conditions, especially when the cooling time is really short, and it's known to form wonderfully vertical motions. But as Natascha has been showing in 2018, if you just have enough azimuthal resolution, like the lower ones here are 360-degree simulations, and this is a 180-degree simulations. In this case, you're actually forming these gigantic anticyclonic vortices. And from the left to the right, this is a time series. And then you see that over hundreds of orbits, these vortices stay there. They are not hampered by the sometimes feared elliptic instability or something like this, but they are really gigantic storm systems. Maybe they are even much closer related to the red spot than we even know today. And of course, the red spot on Jupiter lives for hundreds of years, at least. So vertical shear instability, I said before, operates the best if cooling times, thermal relaxation, is really fast in a disk. If cooling time is longer, then we also came a few years ago to another instability, which is a convective overstability. In that case, it's a radial, we thought. We will change this a little bit. The radial entropy gradient in a disk, which is driving convection. So entropy gradients pointing in the same direction as pressure gradients is what makes your water, your spaghetti water, bubble if you put it on the oven, because you're heating from below and there it's hotter, more entropy, and the pressure is higher, and then you have convection. So this is now a numerical simulation, but not a numerical simulation of the entire disk. You see here roughly the temperature gradient, but it's just a simulation of a small patch of the atmosphere. We do this for two reasons. A, it's cheaper and we have better resolution. And the second thing is that the growth rates, as I will show later, depend pretty much on where you are on the disk. And if you have a large region of a disk, then you have a mismatch of many, many different growth times. But if you have a small region, you can expect that the growth time is relatively constant over the entire system. What I'm plotting here is now the perturbation of temperature after 188 orbits. You see it's a pretty slow growing instability. Then you see that there are actual individual little cells in there which are rotating and messing up with the entropy profile. And this is now a convective mode. I'm doing a flash forward, and you see that these modes are of course growing by getting larger. So the typical modes of this convective overstability is to have this slender convection cells in here. What I'm plotting here is just the velocities. You can see this as streamlines. But the pattern in which these convective cells are ordered are given by the vertical shear instability. That's really funny. So there must be some interaction between convective overstable modes and vertical shear modes. So, and this is now a dispersion relation, which is not only for convective overstability, but simultaneously for vertical shear instability for a given thermal relaxation time, tau. And the control parameters is here this nk square. It's the Brent-Weisseler frequency, giving you the strength of buoyancy. And in the front term here, you have the radial epicyclic frequency, which is giving you stability. And you have the vertical epicyclic frequency, which is an expression for the vertical shear of the system. And now you see that you have the wave numbers in it, vertical and radial wave numbers. And the same is true here for the Grundweißler frequency. But there it's a rather complicated expression. So the Grundweißler frequency in a certain direction of a wave number. So it's not the radial Grundweißler frequency, it's not the vertical, but it's a projection of the buoyancy in this given k direction. So the interesting thing is now that one is having this joint dispersion relation for the convective overstability and at the same time for the vertical shear instability. So if you solve this then and simplify it, then you first can define a growth rate 0, which is 1/2 pressure scale height ratio multiplied by the radial temperature gradient Q. And this gives you the already published, well-known vertical shear instability for instantaneous cooling. If you're then interested in cooling time beyond a certain threshold, which was investigated by Lin and Yudin, then we see that the local growth rate, meaning these are, instead of fundamental modes, just some little local vertical shear instability modes, therefore the L local VSI, smaller modes, then we see that they are scaling with this set gamma 0 squared, and divided by 1, and gamma 0 squared, this is just for the case that, that we are at 0 cooling. And for long cooling time, this is now basically then proportional to gamma 0 squared divided by cooling time. Wonderful. So, and if we are looking for modes of the convective overstability in the same dispersion relation, then we find the same gamma 0 squared, a very similar tau, but in just a slightly different scaling. So, but if you go here for very large tau values, you see that both are almost identical by the small correction that here is a 1/2. And you see here in this lower plot growth times as a function of your cooling time, expressed as cooling times times adiabatic index and Keplerian frequency. And you see here blue lines which are indicating different heights. These are the growth rates of the vertical shear instability. And here you have this small area, this triangle, which are the growth rates of convective modes. And if you go to very short cooling time, then you have basically only here vertical shear instability. And if you go for longer cooling times, then you find here basically this factor of 2, which I've been mentioning before. So growth rates for both kinds of modes in the same order. Vortices are being triggered and zonal flows do form in this idealized simulation of the vertical shear instability with just one fixed cooling time. But of course, a disk around a young star does not have one fixed cooling time. Cooling time is given by radiative processes. So heat first has to diffuse through your optical thick parts, then it has to be radiated at the photosphere, and if you're cooling, then you're cooling the dust grains. So also the coupling, the thermal coupling between dust and gas has to be provided by collisions. And this means that in the midplane, you're not cooling so well because there you're limited by the optical depth. Also in the high atmosphere, you're not cooling that well because collisions between dust and gas are really rare, but they are somewhere in optimum range. So somewhere where the disk is starting to be optical thick and still enough collisions occur between dust and gas. So Thomas Pfeil has been putting this into a prescription of cooling times, calculated here for a pretty far in region. So for normal VSI simulations between 3 and 7 astronomical units, and you see the wonderful formation of vortices and typical VSI modes. So it's really good news to see that in fact, vertical shear instability-like modes do actually operate here in planet-forming interesting region. Natasha Manger has not only been looking for the formation of vortices, she has also studied how strong actually the Reynolds stresses are as a function of the disk temperature. And in a follow-up work, which is right now also on AstroPH available, there you find also the dependence then on Q square being the the radial temperature gradient. So what you see here is now a 1D viscous evolution simulation in which the alpha value, this is the red line here, the deviation from the standard value of 10 to minus 3, is calculated based on the local temperature gradient and based on the local H over R. And as alpha is telling you how much heating you have, of course, this influences the temperature. The temperature influences the local opacity. And again, the opacity has a feedback on the temperature. So you have now a very interesting region here inside, let's say, 10, 12 AU, where you have these thermal instabilities occurring, provided that the outer disk is massive enough to give you the sufficient accretion rate. So, as I said, we are forming rings, zonal flows. And Daniel Carrera has been investigating in a nice collaboration what happens to pebbles drifting through such pressure bumps. You see here the pressure bump structure. The radial drift velocity is smaller than far away from the pressure bump, indicating that that actually here is the pressure maximum, but it's not strong enough to trap off all the particles, but they are changing their drift velocity. They are slightly enhancing in here, and you see here that after some time, then on the way into the pressure bump, you are forming here wonderfully planetesimals, which would not have occurred without the existence of that pressure bump. So if you have no pressure bump and just rely on streaming instability, then you need a certain metallicity. But if you have a pressure bump, it helps you to increase the metallicity so much that you can still trigger it. That there is radial structure and densities, that your pebbles start at some distance to grow, and this is their density at which they are initially available. And then if in the disk there are these pressure bumps, which also Daniel is exploring, and it could be a vortex as well. For a dynamicist, it's basically the same structure. A vortex is just a pressure bump which is not completely axisymmetric. So, and if you are then trapping your pebbles in these zonal flows and vortices, then you are getting to densities where the streaming instability is important. And if you have sufficient density, then, and mass reached, that's important, then you're forming here a planetesimal. So a simulation which I can't to stop here is that material, which is pretty small, Stokes number of 10 to minus 2, and you see how it slowly, these pebbles are contracting, so they have to fight against the ambient turbulence, which is triggered by themselves, so you cannot have a straight collapse. The streaming instability in here is providing you some diffusion, and only if you are beyond a certain threshold, then you form this little guy in here. So this is what we had been showing in these two papers last and this year, that we have now the idea that you can formulate basically a kind of Jeans criterion, so on whether it's possible to form planetesimals or not. So this is a big cloud which you have here, and in that the thermal pressure, or in this case here the diffusion, is not strong enough to prevent collapse. And therefore it collapses. But if you have a small pebble cloud, then the gravity is not strong enough, and then the turbulent diffusion will simply destroy it. So two things. So the bigger object has stronger gravity, and the smaller object has stronger gradients and therefore stronger diffusion. So it's a double effect, which is both preventing two small pebble clouds to collapse. So this should help us to understand what kind of sizes are possible. So of course you can do direct numerical simulations like here by Min Kai and colleagues, where you have just a big box, you're forming thousands of planetesimals, and then you're checking what their size is. And in the beginning it looked like that you are just getting a power law out of it. But meanwhile, by having more and more resolution, there seems to be a particular size favored in the distribution. We're doing streaming instability and gravity simulations of very small scales. And inside these boxes, we are then doing three-dimensional simulations and asking whether they are able to collapse or not. And we found, for instance, then that the diffusivity generated by the streaming instability scales proportional delta, proportional to the Stokes number of your particles, and scales also with epsilon Hill. And epsilon Hill is the dust to gas ratio, which you need in order to have your dust particles, the pebbles, at Hill density, so that the tidal forces can no longer destroy your object. And this helped us to formulate a length scale, a critical length scale for planetesimal formation, scaled on the pressure scale height and based on this streaming instability, diffusivity, and the Stokes number. And I'm not going to bore you with more movies. You can talk to me about this later. We were having this criterion and tested this in a lot of simulations, and it was actually holding pretty well. So we did then some more analytic work here and trying to understand what happens actually in three-dimensional cases. Many of our simulations had been two-dimensional before, and this was getting a little bit tricky because the actual diffusivity that we have in three-dimensional streaming instability simulations is not isotropic, something which was known before, but there it was not so important. But here, if you want to have a criterion of gravity versus diffusion, then it's a little bit more complicated to then basically not have a Hill sphere or a Bonner-Ebert sphere, which is in equilibrium between gravity and pressure or diffusion, but these are actually ellipsoids, out of which then the planetesimals will form. And what you see up here is now the expression of the mass of such a typical Bonner-Ebert sphere, which would be gravitationally unstable. And we were translating this into sizes and testing our criteria and found then that for reasonable parameters you find indeed sometimes like 100-kilometer sized objects. The Bonner-Ebert sphere also has this funny property that of course you can also make smaller masses collapse if they are sufficiently centrally condensed. And that's basically now why this does not occur in our simulations and maybe also not in nature, because if you want to have a planetesimal 1, 2, 3, which is here just by a factor less than 2, larger, or in the other way from M2 to M3, by a factor of 2 smaller, you need a central concentration, a density peak, which is 10 times larger. And this is still a little bit a problem because the pebbles we find are rather large, especially initially, and much larger than the tiny black peppercorns which were found in meteorites. So if this holds true, then this would mean that pebbles, which were not at 1 million or 2 million years, but really at the first 100,000 years of the lifetime, should have been much larger. The implications for planetesimal sizes can be shown here. If you use a normal solar nebula, then planetesimal sizes in the inner part might be 10 kilometer, further out 100. If you are increasing the mass of the nebula, planetesimals will become larger. If you, instead of using a power law, you're using this most appealing nebula, you get a bend law, there's a maximum size, and where outside there is no gas anymore, again you will be forming smaller objects like comets or Kuiper belt objects. Again, if you decrease the mass of the nebula, again you can form smaller things, and if you again decrease the mass, you can after a long time form even much smaller planetesimals out of there. So the prediction is basically that then planetesimal size is a function of distance to the star and also of the mass of the gas nebula. Okay, then we will have later to work on this. Now just a final step. We are now forming planetesimals based on a prescription of pebble flux, and we give them a certain initial size, and we can put them in a numerical simulation, in an n-body simulation done with the LiPad code in collaboration with our friends in Boulder, Herr Leveson, and most importantly, Rogerio Dayeno, who's doing all these simulations here together with Oliver Völk. And there we are putting in pebbles and putting in the planetesimals. And then you see that over time here, then embryos are forming and interacting and pebbles getting accreted and so forth. And then Oliver has been trying to find an analytic prescription for the outcome of the LiPad simulations based on the abundance of planetesimals locally, when and after what time and where the embryos should occur. And he has been putting this into a planet formation model. So in this planet formation model, based on the model tools they developed in Bern, we have now then included the evolution of dust to pebbles by the 2-poppy method, from pebbles to planetesimals with our prescription, and with the additional prescription then from planetesimals and pebbles to embryos. And the first funny thing we found is that we are now not, as in the past was done, have to inject our embryos at whatever place we like, but that they are automatically put at various locations and various times in the code, depending on how many planetesimals are locally available and whether tidal forces by some existing objects allow for the formation of additional objects. And then you see that actually the introduction of embryos occurs at various times and phases. So the first embryos which are forming after a really short time, they are growing really fast by pebble accretion, migrate inwards, some of them disappear in the star. A second generation there, you have some survivors, their pebble contribution is already a little bit less, and then when they are forming these kind of super Earth, mini Neptune things in that kind of particular simulation, then you have in the end even the formation of terrestrial planets at a very late stage, just from the remaining planetesimals in here. So, and here you see the masses which you're getting out of there. So, as I said before, here are some kind of mini Neptune super Earth planets in the inner part, and here these things are all in the Earth and slightly super Earth, and here maybe in the Mars range of objects which are in there. Well, this is not yet a solar system. Additional effects still have to be included, but at least we have now some physics in which was never in there before. So, to come to my conclusions, I think we are seeing a lot of improvements in our understanding of the fundamental processes which are leading to planet formation. So really fundamental processes. So I'm not arguing for an entire planet formation scenario, but we are really improving individual tiny steps. This is that hydroinstabilities do operate in wide ranges of the disks, not only in selected zones. And especially if instabilities, VSI, are not fully fledged, destroying everything and preventing gravitational instability and streaming instability, but are just moderately, gently changing a small wind. And then this leads to zonal flows, vortices, and you can happily form as many planetesimals as you like. So in these zonal flows, if you have them, as I said, you can form planetesimals without boosting the pebble content of the disk. The initial mass function of this planetesimal formation, I think, one can understand as a kind of Jeans mass. So that something between 10 and 100 kilometers can be estimated just by knowing what is the local gas ratio, dust to gas ratio, at pebbles reaching Hill density. And this is nicely to be checked in future investigation, correlations between age of planetesimals, when did they form, and where they are found these days. Okay, and I think we are able to close one of these blind spots in many planet formation models, in population synthesis models, that we can create our own embryos. We don't have to roll the dice and put them somewhere. No, they are consistently formed, as much as we know, with the occurrence of planetesimals and pebbles, and this without any magic intervention. And I think this is roughly what I want to tell you. And I'm looking forward to hear your questions and comments when we meet on Friday in this wonderful session. So thanks a lot. All the best. Stay healthy. Your Hubert Klahr. Bye bye.